let's get into the details of the approximation that naive Bayes makes. So what we are trying to calculate is this: probability of status equals delay given the values of the predictor attributes. This is what you're trying to calculate, right? So effectively we are saying probability of delay given this. I'm just writing it like this so that this is a little more concise. Probability of delay given Monday 3 p.m. DCA EWR UA good. Okay, and now let's recall Bayes' theorem, which said probability of A given B is probability of B given A times probability of A divided by probability of B. Okay, this was our Bayes' theorem. So now we are looking for probability of delay given some attributes B, right? We can invert that and do this, right? So we are saying probability of delay this. By applying Bayes' theorem, we can say is probability of Monday 3 p.m. DCA EWR UA good given delay times probability of delay. Okay, so that's what we want. Now, of course, divided by probability of this. Of course, we can do this only if we are able to calculate this conditional probability and we are able to calculate this probability. Okay, unfortunately, the whole premise of naive Bayes is we may not have enough rows in our data set that match this condition, right? So how are we going to calculate these two probabilities, given that that combination may have very few rows in the data set or may not even occur in the data set? How are you going to do this? That is where the approximation comes into play, right? So what we are going to do is to calculate this probability of this Monday 3 p.m. DCA EWR UA good given delay. We're going to approximate this. This we can do. Probability of delay, very easy, right? Because we've got, let's say, a data set with 2,200 rows, out of which there's a certain proportion which is delayed and certain proportion which is not delayed. So from that we can get the probability of delay. This is easy, right? So in order to do this, the curse of dimensionality poses a real threat that we won't be able to calculate this. Okay, so this is where we are going to approximate, right? So we are going to approximate for both of these by assuming that each of these is independent. In other words, probability of Monday given delay is independent of probability of 3 p.m. given delay, which is independent of probability of the DCA airport given delay, right? So we are breaking it up, assuming that all of these are independent. In reality, they're not. Okay, that is why this is an approximation that we are doing. Okay, similarly, this thing, probability of Monday 3 p.m., we are going to pretend that each of these is independent of the other and simply calculate the individual probabilities and multiply them. Okay, so that is what the naive Bayes is all about. Naive Bayes method is all about. We are creating an approximation for these probabilities. Okay, so we are going to say this probability of Monday 3 p.m. DC is nothing but these individual probabilities multiplied, and these individual probabilities we can easily calculate because of the proportions in the data set. We've got 2,200 rows of data, out of which there are many rows for Monday, so we can calculate probability of Monday. There are many rows for 3 p.m. We can calculate probability of 3 p.m. So this probability we can calculate through this approximation. It's only an approximation because they are in fact not independent. We'll just pretend that they're independent. That's why I've got the approximately equal to sign here. Similarly, for the conditional probability, we're going to pretend that each of these conditional probabilities is independent of the other, and we're going to calculate it like this. Okay, so this is where the approximation comes into play. Okay, and that is how naive Bayes works. It uses these approximations, and once we make these approximations, it can calculate the probability that we were looking for, namely this probability, right? Probability of delay given all of these. This is what we are trying to calculate, and we were saying, well, we don't know how to calculate this because there may not be enough data. Well, with the approximation, we can calculate this, and that'll do the job. Once we have the probability, of course, we can then use a cutoff. We can use the ROC chart, select a cutoff, make a classification. It's all good. Okay, so that's what the naive Bayes approach is all about.